So our next lecture in Unit 5 on modern physics is mass-energy equivalence. It's section 11.4 from your textbook. And this is the last lecture in the special theory of relativity section of this unit. So we've talked about how the special theory of relativity changes our understanding of time, length, and energy, and mass, rather. But we know that mass and energy are connected through E equals mc squared. So there's that mass-energy equivalence. Now, what effect does special relativity have on that relationship? We're going to look at that in this lecture. Now, we're going to start with looking at just the simple E equals mc squared equation, and then we're going to look at the relativistic version of that equation. So this slide here says that the Newtonian definition of work, which is measured in joules, so it's a measurement of energy as well. The mass of an object remains constant, and any energy transferred to increase its kinetic energy results in an increase in speed only. So remember how when we were looking at work, the constant is mass in that case. So if we increase the energy of something, its mass doesn't increase, its velocity increases. So the expectation is that remains valid for any sort of continuous net force. But as soon as we start to approach relativistic speeds, what ends up happening is that our velocity is getting closer and closer to c. We can't hit c because c is our universal speed limit. So we have to have an increase in mass instead. So that is that's how we increase our work done. Using that understanding, this is where Einstein came up with his famous equation that if the mass has to increase because we can't increase our speed anymore, that energy and mass must be related, and they're related in the equation E equals mc squared, where m is the relativistic mass, and that relativistic mass is equal to the proper mass divided by the relativity factor of square root of 1 minus v squared over c squared. So usually when we look at that E equals mc squared equation, we don't write these subscripts. But technically, it's the total energy is equal to the relativistic mass times the square of the speed of light. Although, when we have an object that is not moving, we could still use this equation. It's just that our relativity factor becomes 1. So it makes it the more simple E equals mc squared equation. So I'd like you to copy this down. If you've gone through the review of nuclear physics, which I've asked you to do, you would have also written down the E equals mc squared equation in a previous lecture. So if you're doing this lecture right now and you haven't looked at the nuclear energy or nuclear physics review lecture, please pause and go back, check out that lecture, and then come back here. And remember, when v equals 0, then E equals mc squared. And here you are again. You can write down the rest energy. So this is a different way of referring to that E equals mc squared equation. Technically, when we write it in that form, it's the rest energy. That's the energy of an object at rest. That's when its mass is its proper mass, it's not moving. So the most familiar application of this equation is in nuclear physics. During nuclear fusion, protons and neutrons combine in the interior of the sun to form helium nuclei, as well as the nuclei of other elements. The difference in the masses of the reactants and the products of fusion multiplied by c squared equals the released energy. And we've seen this when we looked at that nuclear physics review lecture as well. You see this when we look at nuclear fission equations or nuclear fusion equations. The energy or the mass lost equals the energy gained, and that mass lost is referred to as the mass defect. But let's look at a question here that deals with the rest energy of a common object that you might, I mean, you've probably seen a cabbage before, so we're talking about a cabbage here. And this is a cabbage that has a mass of 0.75 kilograms. So if we've turned that cabbage, its mass, into pure energy, how much energy would we have? So what we simply do here is it's E equals mc squared. So our m is 0.75. Our c squared is 3 times 10 to the power of 8. And we square that. We're left with 6.8 times 10 to the power of 16 joules. So that's a very large number. You can see it here in non-scientific notation. It has 14 zeros here before it starts to taper off. And how much energy is that exactly? So the next part of this question says that Canada, it takes 3.6 times 10 to the power of 10 joules of energy to power the average home in Canada each day. So if you can turn this cabbage into an energy supply, how many years would we be able to power a home? So let's take this we'll use the more exact value of 6.75 times 10 to the 16 and divide that by 3.6 times 10 to the power of 10. We're left with 1.9 times 10 to the power of 6. That's days. So let's turn that into years. So divide that by 365. We have 5.1 thousand years. So that cabbage can power a home, one home, for 5 millennia. It's pretty powerful. But is that possible? And we don't have a way to directly convert mass into energy. So if we could do that, we could have access to a very large amount of energy. But our world doesn't work that way. It's not just, there's not a machine that just changes mass into energy. The time we have this happening is in nuclear reactions or in relativistic reactions, and those are both very hard to reproduce, especially for something as large as a cabbage. So again, it says here, while most scientists think that mass energy conversion occurs in most processes that release energy, the change in mass that occurs is extremely small. So when we talk about something like energy that we get from combustion, from burning coal, for example, if we had a kilogram of coal and we burn that, there is slightly less than a kilogram left. And it's on the order of 10 to the negative 10 kilograms that is lost. That is such a small amount of energy, even the best electronic balances cannot detect that. So that small mass defect is what gives us our output energy for burning coal. So here's a question. It says that we have a thermal reaction, a chemical reaction rather, and it gives us off 13.8 joules of thermal energy. What does that equal in terms of mass? So 13.8 is our energy. This is the E equals mc squared equation, so I have to just divide this by c squared. So this divided by 3 squared and divided by 10 to the power of 16. That's equal to c squared. So if I divide that, I end up with this value, 1.53 times 10 to the negative, or 10 to the negative 16 it should be, because I did it, I used a negative in there when I did the 16. So that's a very small mass. Now it says, why would a chemist still believe in the law of conservation of mass? And the law of conservation of mass, of course, states that in chemical reactions, the mass is unchanged. And the reason why we can use that in chemistry is because the mass change is so small, it wouldn't even be detected by a balance. So, as you discovered, since the speed of light is a very large number, the magnitude of the rest energy can be very large, even when the rest mass is small. In fact, a rest mass of only 1 kilogram corresponds to a tremendous amount of rest energy. Here we're seeing what is 1 kilogram in terms of energy, and it is 9 times 10 to the power of 16 joules worth of energy. To put that into perspective, the total daily energy consumption for Canada, the whole country, in 2008, was 2.4 times 10 to the 16 joules, which is less than a third of that rest energy. So you can power Canada from 1 kilogram, if you could. 1 kilogram mass could power Canada for an entire day, and then some. So this is why scientists and engineers spend a lot of time and money and energy to look for ways to convert mass into energy. If we can use nuclear energy, we can convert a lot of energy, or very small amounts of mass defect can be converted into very large energies. And even with nuclear fission technology that we have now, it only converts 1% of that of the nuclear energy that's available. And that 1% is an enormous output. So if we can get that better than 1%, nuclear energy provides an opportunity to get a very large output of energy. Of course, there's also the safety and social aspects of it, which we're working on as well. So it says here, since the late 1940s, physicists have looked at ways to produce controlled nuclear fusion reactions, similar to the reactions that produce energy in the sun and other stars. The process also uses the conversion of mass to energy, but uses hydrogen, the most common element in the universe, as fuel. So the sun is a nuclear fusion engine, and it's basically fusing isotopes of hydrogen together to form helium, and as it does that, it outputs a very large amount of fuel, of energy rather. And the fuel, the hydrogen, is actually quite abundant. If we could create a nuclear fusion reaction, and if we could capture that energy very well, we could potentially have a nearly limitless resource of energy here on Earth. Now, this here is a picture of a Tomahawk nuclear fusion reactor. This is a reactor that's being created in, I think it's France or Germany, or it's a combination between the two that are working on it. Nuclear fusion reactions have been studied and partially achieved in devices such as the Tomahawk shown at the right, which uses magnetic fields to create conditions similar to those within the sun. But we haven't been able to capture that energy in a way that is has a positive efficiency value. So right now, the energy we put in to create the reaction is greater than the energy we can get out of the reaction. So one of the advantages of the fusion process is the fewer nuclear or radioactive waste products. So with nuclear fission, the products we have are radioactive, and some of them have quite long half-lives. And because they're radioactive, they can cause genetic damage to living creatures. So that is a problem. But with nuclear fusion, we don't have nearly as many radioactive waste products. So I'd like you to copy this down. The energy production, so special relativity shows that mass and energy are equivalent, E equals mc squared. This is why we convert mass to energy using fission energy. Nuclear fission converts less than 1% of the mass to energy, but it still produces an enormous amount of energy. There are radioactive byproducts, though, which are dangerous and long-lasting. Nuclear fusion provides more energy and fewer radioactive wastes, but the technology is pretty difficult. So that's what we're having, a technological issue with that right now. So let's look at a question here. If we have a piece of uranium and it has a mass of 1,000 100 kilograms, and that's accurate to the nearest 1,000th. And we put this in a reactor. It says 4 years later, the mass has decreased to 99.312 kilograms. So determine the energy that was released during this time. And we're asked to use the more accurate value of C, that's accurate, that's 2.99799 times 10 to the 8. So it's quite accurate value. So we're going to have 6 significant digits for this question. Actually 5, we're limited on the mass. So first we need to find, for a question like this, we need to find the mass defect. And the mass defect, which you would have copied down previously, but I'll write down the equation here. It's the mass of the reactants minus the mass of the products. So please copy this down if you haven't done so already, where MD is the mass defect. And our mass defect for this problem is our reactants were the 100.000 kilograms of uranium, and the mass of the products, so what's left over, is the 99.312 kilograms. So this works out to 100 minus 99.312, 0.688 kilograms. And now we need to find how much energy this is. So this is our MC squared. So 0.688 times 3 times 10 to the 8 squared. So if I take this value and multiply it by 9 times 10 to the power of 16, which is what our C squared is equal to, I'm left with, oh, you know what, I'm sorry, I should use the more accurate value. So 0.688 times 2.99799 squared times 10 to the power of 16. I'm left with, using 5 significant digits, 6.1837 times 10 to the power of 16 joules as my solution. Now let's look at another problem. This one's going to look at relativity. So here it says a car requires, no, it's not going to look at relativity. It says a car requires 1 times 10 to the 8 joules of energy to drive 30 kilometers. Calculate how many kilometers you can hypothetically drive using the energy contained in 100.0 milligrams of fuel. So here our mass defect would be the 0.1 kilograms of fuel. So our E equals MC squared. Our 0.1 times 3 times 10 to the 8 squared. Oh, sorry, it says it takes that much energy to drive 30 kilometers. I'm doing this a bit, so I could find the energy first, and then we're asked how many kilometers we can drive. So 0.1 times 9 times 10 to the power of 16. This is how much energy I have. E equals 9.0 times 10 to the 15 joules. Now, I know it takes me 1 times 10 to the 8 joules of energy to drive 30 kilometers. So, how much, what I need to do is basically divide this by, so I'm going to rewrite this here. I'll do my distance to travel is my energy divided by my efficiency here, which is going to be, I'm going to call this E30K divided by 30K. So this works out to 9.0 times 10 to the 15 divided by 1 times 10 to the 8 divided by 30k, which is going to be 30000. So I'll take this value divided by 10 to the power of 8 and multiply it by 30,000. I end up with, my answer is in meters, so I end up with D equals 2.7 times 10 to the 12 meters, or 2.7 times 10 to the 9 kilometers. So I got quite a bit of range from that 100 milligrams of fuel. So try out the questions in this section. They're actually a bit more difficult than the ones we've done in the lecture. So if you need any help, feel free to ask me questions on the course website.